The rapid acceleration of electric cars, especially Tesla models, results from the synergy of various factors, with a focus on the trio of electric motors and the battery. The company, named in homage to Nikola Tesla, a notable inventor and engineer from the 19th and 20th centuries, is recognized for adopting the induction motor, an innovation by Tesla. His seminal work involved electricity and magnetism, credited with inventions such as the radio, remote control, and the Tesla coil. However, the reason Tesla chose its name is intrinsically linked to the invention of the induction motor, a device powered by alternating current and based on electromagnetic induction. To understand the basis of this motor, it is useful to revisit simple concepts of magnetism. Anyone who has used a compass understands that a magnetized needle points north, aligned with the Earth's magnetic field. Now, introducing a magnet near the compass causes the needle to align with the magnet, indicating a strong magnetic attraction. This phenomenon is exploited in electric motors, harnessing the ability of magnets to attract and repel. Electric motors operate by utilizing this force of attraction and repulsion to spin the rotor. By adding electromagnets to the equation, using conductive materials like copper, we can modulate the magnetic field. Copper, not naturally magnetic, becomes an electromagnet when current flows through it. This dynamic control over the magnetic field is essential for the constant rotation of the motor. In the induction motor, we distinguish two main components, the stator and the rotor. The stator, the outer ring of the motor, consists of coils of copper wire, each being an electromagnet. The rotor, located in the center, is a core of iron surrounded by permanent magnets. By energizing the coils in a controlled manner, it is possible to create a rotating magnetic field, generating the movement of the rotor. This principle, though complex, proves fundamental to the exceptional acceleration of Tesla electric cars. The secret to maintaining continuous rotation in the induction motor lies in the constant movement of the north and south poles of the stator magnets around the outer ring. This process is controlled by the direction of the electron flow in the stator wire coils. By circulating the south pole of the stator in a circle, it attracts the north pole of the rotor, while simultaneously the south pole of the stator pushes the south pole of the rotor. This continuous force of attraction and repulsion rotates the rotor, and the faster we move the magnetic field around the stator, the faster the rotor spins. Examining the Tesla logo, we notice a graphical representation of this electric motor, where the upper curved line represents the stator ring, and the pointed T shape is a cross-section of the rotor. This configuration is crucial for understanding the motor's design. The simplified explanation of how the induction motor works leads us to the understanding that, to maintain rotation, a constant displacement of the magnetic poles is necessary. The efficiency of this mechanism is evidenced by the Tesla logo, visually encapsulating the induction motor. Now, focusing on the Tesla Plaid electric motor, its uniqueness goes beyond the simple addition of a third motor. The distinctive feature lies in the rotor, which features a carbon sleeve, an innovation highlighted by Elon Musk. Traditionally, a rotor would have a steel sleeve, but the Plaid utilizes a carbon fiber sleeve, a novelty introduced by Tesla. This carbon sleeve consists of a tight winding of carbon fiber threads, saturated with epoxy to solidify into a cohesive mass. The winding process occurs under extreme tension, requiring a machine specially designed by Tesla to apply sufficient force. The reason behind this meticulous process is the counteraction of the rotor's shrinkage in low temperatures, preventing potential separations. Additionally, carbon helps maintain the stability of the rotor, preventing unwanted expansions caused by centrifugal force at high speeds. The ability of the carbon fiber casing to contain the expansion of the rotor is crucial to maintaining the minimum distance between the rotor and the stator. This allows optimizing the force of attraction and repulsion between the magnets, maximizing the efficiency of the Tesla Plaid electric motor. This innovation in rotor design is one of the reasons the vehicle achieves exceptional levels of performance and speed, standing out among its competitors. The difference between exceptional and optimal performance in Tesla's electric motors lies in minuscule details on the order of microns. Despite its small size, this measurement plays a crucial role in the pursuit of maximum power across the motor's performance spectrum. This precision allows Tesla to maintain a consistent power delivery across all ranges, an achievement previous models often struggled to accomplish. A team of professionals, specialized in vehicle disassembly and analysis, provides a unique insight into what comprises the Tesla Model S Plaid motor. The fascinating disassembly journey reveals the inverter as the motor's brain, controlling the flow of electricity into the magnets and thus regulating the motor's speed and operation. Remarkably, the inverter board in each Model S Plaid motor bears the inscription Model 3, indicating surprising uniformity across all Tesla motors, regardless of the model. The uniqueness of the Model S Plaid is enhanced by a specific modification to the inverter board, the addition of an explosive fuse. When activated, this component acts as a kind of tiny bomb, physically breaking the connectors of the electrical bus and instantly interrupting the electrical connection of the motor in extreme situations. A striking safety measure, highlighting Tesla's concern for vehicle safety. Another highlight of the analysis reveals that the three motors in the Model S Plaid are identical. This choice reflects production efficiency, simplifying the process and ensuring uniformity in all components. The advantage of having two motors at the rear is explained, not only for providing more power but also for simplifying the design. By using one motor per wheel, the need for a differential is eliminated, reducing opportunities for energy loss due to friction or gear sets. The single gearbox between the Plaid motors and the rear wheels is a necessity, as Tesla opts not to include a transmission. This, in turn, imposes a specific gear ratio on the Plaid motor, with a reduction of 7.54 to 1. This ratio differs from the standard model, such as the Model Y, which has a ratio of 8.996 to 1. Examining the internal components of the Plaid motor, the rotor stands out, where Tesla implements star-shaped laminated sheets to form the iron core. These blades, totaling 529, create 6 rows of magnets around the rotor. The innovative design includes a unique assembly and a laminated cover that resembles the Tesla logo. These surprising findings provide a deeper insight into Tesla's commitment to efficiency and innovation in its electric motors. The construction and floating caps of the checkerboard rotor contribute to a notable 25% increase in power and torque capacity. Additionally, the permanent magnets used in the Plaid's rotor are substantially more powerful than those found in conventional electric motors, surpassing even Tesla's standard motors. In an informal test, the force required to separate a bolt from the Plaid rotor's magnets was measured. Comparing the results between the Model S Plaid, a Model Y, a BMW i3, and a Mustang, it was found that an impressive force of 151 newtons was required to remove the bolt from the Plaid rotor. In contrast, the Model Y required 112 newtons, the BMW i3 needed 93 newtons, and the Mustang only 81 newtons. This difference indicates that the Plaid's rotor magnets are almost twice as powerful as those of the simulated electric Mustang and over a third stronger than those of the Model Y or Model 3 rear motor. Understanding these nuances adds an extra layer of fascination for electric car enthusiasts. When we talk about the power of the Plaid motor, we're not just making a boast. The resistance of this motor to significant forces is something worth highlighting. Compared to other electric motors, the Plaid demonstrates its robustness, its ability to withstand extreme conditions and challenges that other motors may face. In summary, we are witnessing Tesla's smart efficiency in sharing crucial components, combined with the robust strength of the Plaid motor, which goes beyond mere performance to withstand unpredictable challenges. This is Tesla's hallmark, a unique combination of efficiency, innovation, and resilience that redefines our expectations of what an electric vehicle can achieve.